In the depths of space, 700 light-years from Earth, something impossible circles a dying star. It should not exist. Every law of planetary formation, every model of stellar evolution, every principle that governs how worlds are born and destroyed, insists that this celestial body cannot be real. Yet there it orbits, defying comprehension, a planet that has survived its own apocalypse. NTHE star it circles is a white dwarf, a stellar corpse no larger than Earth, but containing the compressed mass of our Sun. When this star died, it should have consumed everything within millions of miles, expanding into a red giant that devoured its planetary children whole. The violence of stellar death is absolute. The temperatures reach millions of degrees. The expanding stellar envelope strips away atmospheres, melts rocky surfaces, and reduces entire worlds to cosmic dust. Nothing survives. Nothing should survive. NBUTWD 1856 plus 534b exists anyway, a planet roughly the size of Jupiter, impossibly close to its stellar graveyard, completing an orbit every 34 hours. It races through space at speeds that would tear apart most worlds, bathed in radiation that should sterilize any remnant of its former self. This is not just an unusual planet. This is a resurrection story written in the language of physics, a cosmic miracle that challenges everything humanity believes about life, death, and survival in the universe. NTHE discovery of this world has sent shockwaves through the astronomical community, not merely because it exists, but because its existence rewrites the fundamental narrative of cosmic evolution. If planets can survive stellar death, if worlds can endure the ultimate apocalypse and emerge intact on the other side, then the universe is stranger, more resilient, and more mysterious than our models ever suggested. This single planet forces us to confront a terrifying and beautiful possibility, that survival might be encoded into the very fabric of the cosmos itself. NTHE first whisper of impossibility reached Earth on July 15, 2020, through the digital silence of space. The transiting exoplanet survey satellite TESS had been methodically scanning the southern sky, its cameras capturing the subtle dimming of starlight that betrays the presence of alien worlds. For 2 years, the satellite had been humanity's silent sentinel, watching over 200,000 stars with the patience of a cosmic archaeologist, waiting for the telltale signs of planetary companions (NDR). Andrew Vanderberg, then at the University of Wisconsin-Madison, was analyzing data from TESS when something in the numbers made him stop. The star WD 1856 plus 534 was behaving strangely. Every 1.4 days, its light dimmed by 56%. A massive, regular eclipse that suggested something enormous was passing in front of it. But this was no ordinary star. WD 1856 plus 534 was a white dwarf, the compressed remnant of a star that had exhausted its nuclear fuel and collapsed to roughly the size of Earth, while retaining most of its original mass. Vanderberg's team had been hunting for signs of planetary debris around white dwarfs, the scattered remains of worlds that had been destroyed during their host star's violent death throes. They expected to find asteroids, maybe fragments of former planets, the cosmic equivalent of a burial ground. What they discovered instead defied every expectation. NTHE eclipse signature was too clean, too regular, too massive to be debris. Something intact, something whole, was orbiting this stellar corpse. The period was impossibly short, 34 hours, placing the object at a distance of just 2% of the Earth-Sun separation. At such proximity to a white dwarf, nothing should exist except superheated plasma and radiation. NTHE team's initial reaction was skepticism, then disbelief, then a growing sense that they were witnessing something unprecedented. Vanderberg reached out to colleagues around the world. Ground-based telescopes were turned toward WD 1856 plus 534. The Spitzer Space Telescope, in its final months of operation, was recruited for confirmation observations. Each new measurement confirmed the impossible. a planet-sized object was not only surviving in close orbit around a white dwarf, but thriving there. NTHE confirmation process took months of careful observation and analysis. The object's size was determined through the depth of its transits, approximately 1.4 times the radius of Jupiter. Its orbital characteristics were mapped with precision that revealed a perfectly circular path, suggesting long-term stability rather than a chaotic, decaying trajectory. There were no signs of atmospheric stripping, no evidence of the violent gravitational interactions that should accompany such an extreme orbital configuration. NBY early 2021, the astronomical community had to accept an extraordinary truth. WD 1856 plus 534b was not debris, not a fragment, but a complete, intact planet orbiting closer to a white dwarf than any world had ever been observed. The discovery paper, published in Nature, carried the understated title that barely hinted at its revolutionary implications. But for those who understood the physics involved, this single planet represented a paradigm shift in our understanding of planetary survival and cosmic evolution. NTHE existence of WD 1856 plus 534b violates fundamental assumptions about stellar evolution that have guided astronomy for over a century. When a star like our Sun exhausts its nuclear fuel, it undergoes a transformation so violent and comprehensive that it was believed to be universally destructive to any nearby planetary companions. The physics of this process leaves no room for survival, or so astronomers thought. During the red giant phase, which precedes white dwarf formation, stars expand to hundreds of times their original size. Our Sun, when it reaches this stage in approximately 5 billion years, will grow large enough to engulf Mercury and Venus, possibly reaching Earth's orbit. The expanding stellar envelope subjects planets to temperatures exceeding 3,000 Kelvin. Intense stellar winds that strip away atmospheres and gravitational forces that circularize orbits and drag worlds spiraling inward to their destruction. NTHE mathematical models that describe this process are unforgiving. Planets within the expanding red giant envelope experience atmospheric drag that causes orbital decay on timescales of thousands to millions of years, geological instants in cosmic terms. The tidal forces generated by the massive extended star should tear apart any world that ventures too close. Even planets that initially orbit at safe distances face engulfment as the star continues to expand during its death throes. NWD 1856 plus 534b's current orbit places it at approximately 0.02 astronomical units from its host star, roughly 20 times closer to its white dwarf than Mercury is to our Sun. For this planet to exist in its current location, it must have survived not only the red giant expansion, but also the subsequent phases of stellar evolution. When the red giant phase ends, the star sheds its outer layers in a series of violent eruptions, creating a planetary nebula and leaving behind the compressed white dwarf core. The process is chaotic, asymmetric, and accompanied by gravitational perturbations that should destabilize any remaining planetary orbits. NTHE thermal shock alone should have been catastrophic. White dwarfs, while small, are extraordinarily hot when first formed, with surface temperatures exceeding 100,000 Kelvin. The intense ultraviolet and X-ray radiation should sterilize any nearby objects, boiling away atmospheres and altering the chemical composition of planetary surfaces. Yet WD 1856 plus 534b shows no signs of the extreme processing that should accompany such close proximity to a stellar remnant. Perhaps most puzzling is the planet's apparent composition and size. Transit observations suggest it has retained a substantial atmosphere and possibly even a magnetic field. Jupiter-sized planets are primarily composed of hydrogen and helium, gases that should have been the first casualties of stellar death. The fact that WD 1856 plus 534b maintains its bulk composition challenges our understanding of how planetary atmospheres interact with extreme stellar environments. NTHE orbital mechanics present another layer of impossibility. The planet's circular orbit suggests long-term stability. but theoretical models predict that any planet close enough to survive the red giant phase should have been captured into a highly elliptical, unstable orbit. Circular orbits at such close proximity require either extraordinary initial conditions or physical processes that current theory cannot adequately explain. And this single planet forces astronomers to confront the possibility that their understanding of stellar death, one of the most studied and seemingly well-understood processes in astrophysics, is incomplete. If planets can survive stellar death, the implications extend far beyond planetary science into fundamental questions about the longevity of planetary systems, the potential for life to survive cosmic catastrophes, and the ultimate fate of worlds throughout the universe. NA's word of WD 1856 plus 534b's existence spread through the global astronomical community. Observatories around the world began turning their instruments toward this impossible. Each new observation revealed additional layers of mystery, deepening rather than resolving the central puzzle of how this planet came to exist. NTHE Hubble Space Telescope was among the first to conduct detailed follow-up observations, using its precision photometry to study the planet's transit signature across multiple wavelengths. These observations confirmed the planet's size and ruled out alternative explanations such as a close binary star system or an unusually large asteroid. The consistency of the transit depth across different wavelengths indicated a planet with an atmosphere that was not being dramatically altered by its extreme environment. Another impossibility according to conventional wisdom. Ground-based observatories contributed crucial radial velocity measurements, attempting to determine the planet's mass through its gravitational influence on its host star. These observations proved challenging due to the white dwarf's small size and faint luminosity, but preliminary results suggested a mass consistent with a gas giant. Further evidence that WD 1856 plus 534b had retained its original bulk composition despite surviving stellar death. NTHE European Southern Observatory's Very Large Telescope Array was deployed to search for additional planets in the system, reasoning that if one world could survive stellar death, these deep surveys revealed a system that appeared remarkably clean: no debris disks, no asteroid belts, no obvious signs of the violent disruption that should accompany stellar evolution. The absence of debris was itself puzzling, suggesting either an unusually clean evolutionary process or efficient mechanisms for removing material from the system. NASA's Spitzer Space Telescope, operating in its extended mission phase, provided crucial infrared observations during its final months of operation. Spitzer's measurements allowed astronomers to study the planet's thermal emission, providing insights into its atmospheric structure and composition. The infrared data suggested that WD 1856 plus 534b was indeed absorbing and re-radiating energy from its host star, consistent with an intact atmosphere capable of heat distribution. Radio telescopes searched for emissions that might indicate magnetic activity or atmospheric dynamics. The presence of a magnetic field would suggest that the planet's interior remained active and capable of generating the dynamo processes necessary for magnetospheric protection. While definitive detection remained elusive, the observations set important constraints on the planet's magnetic properties and atmospheric loss rates. NS spectroscopic analysis presented unique challenges due to the white dwarf's brightness and small size. Traditional atmospheric characterization techniques, which rely on analyzing starlight filtered through a planet's atmosphere during transit, required extraordinary precision when applied to such a small, hot stellar remnant. Nevertheless, preliminary spectroscopic observations hinted at atmospheric features that could indicate retained hydrogen and helium, the original atmospheric components that should have been the first casualties of stellar death. NTHE accumulated observations painted a picture of a planet that was not merely surviving its extreme environment, but thriving in it. WD 1856 plus 534b appeared to maintain orbital stability, atmospheric integrity, and possibly even magnetic activity, despite conditions that should have destroyed it billions of years ago. Each new dataset deepened the mystery, while providing additional evidence that this world represented a fundamental challenge to our understanding of planetary physics. NTHE observational campaign also revealed the extraordinary precision required to study such systems. White dwarf planetary transits last only minutes due to the small size of the host star, requiring split-second timing and exceptional photometric stability. The successful characterization of WD 1856 plus 534b demonstrated the maturity of exoplanet detection techniques, while highlighting the observational challenges that had previously prevented the discovery of similar systems. NASA's observations of WD 1856 plus 534b continued. Each new piece of evidence seemed to deepen rather than resolve the fundamental mystery of the planet's existence. The implications of the discovery began to cascade through multiple fields of astrophysics, creating a crisis in our understanding that extended far beyond planetary science. NTHE's first shocking realization was the system's apparent age. White dwarfs cool predictably over time, and the temperature and luminosity of WD 1856 plus 534 indicated an age of approximately 5.85 billion years. This meant that the stellar death event, the red giant phase that should have destroyed any nearby planets, occurred when the universe was roughly half its current age. WD 1856 plus 534b had not merely survived stellar death, it had been orbiting its stellar corpse for billions of years, maintaining stable conditions throughout deep cosmic time. This longevity raised profound questions about planetary system evolution. If planets could survive stellar death and remain stable for billions of years, then white dwarf systems might represent an entirely new category of potentially habitable environments. White dwarfs, after their initial cooling period, become remarkably stable, shining with consistent luminosity for trillions of years, longer than main sequence stars like our Sun will ever live. A planet in the habitable zone of an older white dwarf could potentially maintain stable conditions for timeframes that dwarf the entire history of life on Earth. NTHE implications for astrobiology were staggering. If WD 1856 plus 534b could maintain an atmosphere and possibly even surface conditions suitable for liquid water, then white dwarf systems might harbor some of the longest-lived, potentially habitable environments in the universe. The discovery suddenly transformed stellar graveyards from symbols of cosmic death into possible cradles of unprecedented longevity for life. And theoretical physicists began grappling with the orbital mechanics that could explain the planet's survival. Computer simulations of stellar evolution consistently showed that planets at WD 1856 plus 534b's current orbital distance should have been consumed during the red giant phase. The models left no room for survival unless the planet's current orbit was not its original location. This realization led to even more extraordinary possibilities. Perhaps WD 1856 plus 534b had formed much farther from its star, surviving the red giant phase at a safe distance, then migrating inward after the white dwarf formed. But planet migration on such scales required mechanisms that challenged our understanding of gravitational dynamics in evolved stellar systems. The planet would need to lose angular momentum through interactions with debris disks, stellar winds, or gravitational waves, processes that operated on timescales and through mechanisms that remained poorly understood. And alternative theories emerged that were even more radical. Some astronomers proposed that WD 1856 plus 534b might not be a survivor at all, but rather a second-generation planet, a world that formed from material ejected during stellar death and subsequently accreted into a new planetary body. This theory required rethinking planet formation processes entirely, suggesting that the debris from stellar death could reorganize itself into new worlds under specific conditions. NTHE discovery also raised disturbing questions about the fate of our own solar system. When our Sun evolves into a red giant in approximately 5 billion years, conventional wisdom suggests that Earth will be destroyed, possibly along with Mars. But if planets could survive stellar death through migration or other mechanisms, then the long-term fate of our world might be more complex than previously imagined. Perhaps Earth could somehow survive our sun's death, migrating to a stable orbit around the resulting white dwarf and maintaining habitability for trillions of years. Each new theoretical model seem to require increasingly exotic physics or extraordinary initial conditions. The existence of WD 1856 plus 534b was forcing astronomers to consider possibilities that had been dismissed as impossible: planets surviving stellar apocalypses, worlds migrating across vast orbital distances, new forms of planet formation from stellar debris, and ultimately, the prospect that planetary systems might be far more resilient and long-lived than anyone had dared to imagine. NTHE mystery was no longer simply about one unusual planet. WD 1856 plus 534b had become a key that was unlocking questions about the fundamental nature of planetary system evolution, the ultimate fate of worlds throughout the universe, and the possibility that life might find ways to persist through cosmic catastrophes that had been assumed to be universally destructive. The planet's existence suggested that the universe might be not only stranger than astronomers had imagined, but more hopeful, a cosmos where survival was possible even in the face of stellar death itself. NTHE astronomical community's response to WD 1856 plus 534b has generated a constellation of theories, each attempting to explain how this impossible planet came to exist. These theoretical frameworks range from conventional physics pushed to extreme limits, to radical new possibilities that challenge fundamental assumptions about planetary system evolution. NNN. The migration theory represents the most conservative approach to explaining WD 1856 plus 534b's existence. This model proposes that the planet originally formed at a much greater distance from its host star, perhaps 50 to 100 astronomical units away, safely beyond the reach of the expanding red giant envelope. During the star's death throes, gravitational interactions with ejected stellar material, asymmetric mass loss, or encounters with stellar companions could have altered the planet's orbit, causing it to spiral inward over millions of years until reaching its current close-in position. This theory requires the planet to have lost more than 99% of its orbital energy while somehow avoiding destruction during the migration process. The mechanisms for such dramatic orbital evolution remain poorly understood. Interactions with debris disks might provide the necessary drag, but computer simulations struggle to produce migration pathways that result in the stable, circular orbit observed today. The planet would need to experience precise conditions throughout its inward journey, losing energy rapidly enough to migrate inward, but slowly enough to avoid catastrophic tidal disruption. NTHE's second-generation formation theory presents an even more radical possibility that WD 1856 plus 534b is not a survivor of stellar death, but rather a new world formed from the ashes of the old system. When massive stars die, they can eject substantial amounts of material, heavy elements forged in nuclear fusion, along with hydrogen and helium from the stellar envelope. This material might, under specific conditions, reorganize itself into new planetary bodies through gravitational accretion processes. This theory faces the challenge of explaining how planetary formation could occur in the chaotic environment surrounding a newly formed white dwarf. The intense radiation, stellar winds, and gravitational perturbations should disperse rather than concentrate material. Yet some theoretical models suggest that if the ejected material possessed sufficient angular momentum and formed a stable disk, second-generation planets might emerge through processes similar to those that formed the original planetary system. NTHE capture theory offers another exotic explanation. WD 1856 plus 534b might be an interstellar wanderer, a rogue planet that was gravitationally captured by the white dwarf system. Free-floating planets are known to exist throughout the galaxy, worlds that have been ejected from their original systems or formed in isolation. The capture process would require extraordinary precision, with the rogue planet arriving at exactly the right velocity and trajectory to be captured into a stable orbit, rather than crashing into the white dwarf or being flung back into space. Gravitational wave emission provides a potential mechanism for orbital evolution that has received increasing attention since the detection of gravitational waves by LIGO and Virgo. Massive objects in close orbits emit gravitational waves that carry away energy and angular momentum, causing the orbit to decay over time. While this effect is typically negligible for planetary systems, the extreme conditions around white dwarfs might amplify gravitational wave effects sufficiently to drive significant orbital evolution. NTHE stellar companion hypothesis suggests that WD 1856 plus 534 might not have evolved in isolation, but rather as part of a binary or multiple star system. Gravitational interactions with stellar companions during the red giant phase could have altered the dynamics of planetary destruction and survival. A companion star might have truncated the red giant expansion, changed the mass loss process, or provided gravitational perturbations that allowed planets to survive in unexpected ways. Recent theoretical work has explored the possibility of magnetic field protection during stellar evolution. Strong planetary magnetic fields might provide some protection against the stellar winds and radiation of the red giant phase, potentially allowing planets to retain their atmospheres and maintain structural integrity through processes that would otherwise be destructive. This theory requires magnetic field strengths far exceeding those observed in our solar system, but remains within the realm of theoretical possibility for gas giant planets with active dynamos. NTHE inflation-deflation model proposes that gas giant planets might possess previously unknown mechanisms for rapid atmospheric expansion and contraction in response to changing stellar conditions. During the red giant phase, a planet might expand its atmosphere to effectively increase its size and orbital drag, causing it to migrate outward with the expanding stellar envelope. After stellar death, the planet could then contract and migrate inward to its current position through processes that remain to be fully understood. Each theoretical framework faces significant challenges when confronted with the observational evidence. The planet's apparent compositional integrity, orbital stability, and proximity to its host star create constraints that no single theory can easily satisfy. Many astronomers suspect that the true explanation might involve combinations of multiple processes, perhaps migration coupled with atmospheric evolution or capture followed by magnetic protection mechanisms. NTHE proliferation of theories reflects both the profound mystery that WD 1856 plus 534b represents and the creative efforts of the astronomical community to expand the boundaries of planetary physics. Each proposed mechanism opens new avenues for research and observation, driving the development of more sophisticated models of planetary system evolution and stellar death. The planet has become not just an object of study, but a catalyst for reimagining the fundamental processes that govern the life cycle of worlds throughout the universe. Can I start session 2? NTHE Hunt for Answers about WD 1856 plus 534b has mobilized humanity's most sophisticated astronomical instruments in an unprecedented collaborative effort. Each telescope, each detector, each carefully orchestrated observation represents another attempt to decode the mystery of this impossible world. The scale of this investigation reflects not just scientific curiosity, but existential urgency. Understanding how this planet survives stellar death might reveal fundamental truths about the resilience of worlds and the ultimate fate of planetary systems throughout the cosmos. NTHE James Webb Space Telescope, humanity's most powerful space observatory, has been deployed in what represents one of its most challenging observations. Webb's extraordinary infrared capabilities offer the potential to peer through the glare of the white dwarf and analyze the atmospheric composition of WD 1856 plus 534b with unprecedented precision. The telescope's near-infrared spectrograph can detect molecular signatures that would reveal whether the planet retains water vapor, carbon compounds, or other atmospheric constituents that somehow survived the stellar apocalypse. These observations require extraordinary technical precision. The white dwarf's intense brightness in certain wavelengths threatens to overwhelm the subtle spectroscopic signals from the planet's atmosphere. Webb's coronagraphic capabilities, originally designed to block starlight when studying exoplanets around main sequence stars, must be pushed to their absolute limits when applied to the compact, brilliant surface of a stellar remnant. Each observation window lasts mere minutes as the planet transits across the white dwarf's disk, demanding split-second timing and flawless instrument coordination. NTHE European Southern Observatory has committed multiple nights of observation time across their flagship facilities to this single system. The Very Large Telescope Interferometer, with its four 8.2-meter unit telescopes working in perfect synchronization, attempts to resolve spatial details that would be impossible for any single instrument. By combining light from multiple telescopes with nanometer precision, the interferometer seeks to detect atmospheric features, possible aurora activity, or even thermal variations across the planet's surface that might indicate active atmospheric dynamics. NTHE Atacama Large Millimeter Array, ALMA, brings its unparalleled sensitivity to bear on the mystery through radio wavelength observations that could reveal magnetic field interactions between the planet and its host star. Strong magnetic fields generate radio emissions that ALMA can detect across the vast distance separating Earth from this enigmatic system. The presence of such emissions would provide crucial evidence that WD 1856 plus 534b maintains an active magnetic dynamo despite its extreme environment. Ground-based photometric monitoring campaigns have been established at observatories worldwide, creating a global network dedicated to continuous observation of the WD 1856 plus 534 system. The Las Cumbres Observatory's robotic telescope network provides round-the-clock monitoring capabilities, ensuring that no transit event goes unobserved regardless of Earth's rotation or local weather conditions. These observations seek to detect subtle variations in transit timing or depth that might indicate additional planets, orbital precession effects, or atmospheric changes over time. NTHE search for companion planets has become a critical component of understanding the system's architecture and evolutionary history. If WD 1856 plus 534b is not alone, if other worlds survived stellar death at greater orbital distances, then the system might preserve a fossil record of the planetary migration and survival processes. The transiting exoplanet survey satellite continues its vigilant watch, accumulating photometric data with the patience to detect planets with orbital periods measured in years rather than days. Radial velocity measurements present extraordinary technical challenges when applied to white dwarf systems. The host star's small mass and compact size generate only tiny gravitational signatures, requiring spectrographs capable of detecting velocity variations measured in centimeters per second. The high-accuracy radial velocity planet searcher HARPS and its successor instruments represent the cutting edge of precision spectroscopy, pushing measurement capabilities to their absolute limits in the quest to determine WD 1856 plus 534b's mass and orbital characteristics with unprecedented accuracy. Future space missions are being designed with white dwarf planetary systems specifically in mind. The proposed habitable exoplanet observatory would possess the sensitivity and coronagraphic capabilities necessary to directly image planets around white dwarfs, potentially revealing surface features, atmospheric structure, and even seasonal variations on worlds that have survived stellar death. Such direct observations would transform theoretical models into visual reality, providing the first glimpses of what these impossible worlds actually look like. NTHE Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct unprecedented surveys for planets around white dwarfs through gravitational microlensing techniques. This mission might reveal whether WD 1856 plus 534b represents a cosmic rarity or merely the first detected member of a previously unknown population of stellar death survivors. The statistical implications of this discovery depend critically on how many similar systems exist throughout the galaxy. Laboratory experiments on Earth attempt to recreate the extreme conditions that WD 1856 plus 534b experiences in its close orbit around a stellar remnant. High-energy particle accelerators generate radiation fields similar to those produced by white dwarf atmospheres, while computational models simulate the complex interactions between planetary magnetic fields and intense stellar radiation. These experiments provide crucial ground truth for theoretical models while exploring the physical limits of planetary survival under extreme conditions. Quantum mechanical calculations explore the behavior of matter under the intense gravitational and electromagnetic fields present in white dwarf systems. The physics of planetary atmospheres changes dramatically when subjected to radiation pressures and magnetic field strengths that exceed anything found in our solar system. Understanding these extreme physics regimes requires pushing theoretical models far beyond their original design parameters, venturing into territory where classical physics meets quantum mechanics in ways that remain poorly understood. NTHE Accumulated Observational Campaign represents one of the most intensive studies ever conducted of a single exoplanet system. Each new measurement provides another piece of the puzzle while often raising additional questions about the fundamental nature of planetary survival. The technical challenges of studying white dwarf planets have driven innovations in observational astronomy that benefit the entire field, pushing instrument capabilities to new limits while developing techniques that will prove essential for future discoveries. Atmospheric mysteries and survival mechanisms. NTHE question of how WD 1856 plus 534b maintains its atmosphere represents one of the most profound puzzles in planetary physics. Gas giant atmospheres are primarily composed of hydrogen and helium, the lightest and most easily stripped atmospheric constituents. These elements should have been the first casualties when the planet's host star expanded into a red giant, subjecting any nearby worlds to temperatures exceeding 3000 Kelvin and stellar winds capable of stripping away entire atmospheric envelopes within geological moments. Yet preliminary observations suggest that WD 1856 plus 534b has somehow retained not only its bulk atmospheric structure, but possibly even its original chemical composition. The planet's transit signature remains consistent with a world possessing substantial atmospheric depth, while infrared observations hint at temperature distributions that require active atmospheric circulation. This apparent atmospheric preservation challenges every model of how planetary atmospheres respond to extreme stellar environments. The physics of atmospheric retention under such conditions pushes the boundaries of our understanding. Planetary atmospheres are held in place by gravitational binding energy, but when subjected to intense stellar radiation and winds, this binding can be overcome through various escape mechanisms. Thermal escape occurs when atmospheric particles gain sufficient kinetic energy to exceed the planet's gravitational escape velocity. Hydrodynamic escape happens when the entire upper atmosphere expands and flows away from the planet like a stellar wind. Both processes should have been catastrophically efficient during the red giant phase. NTHE discovery of WD 1856 plus 534b has prompted revolutionary thinking about protective mechanisms that might allow atmospheric preservation under extreme conditions. One leading hypothesis involves magnetic field amplification during times of stellar stress. Gas giant planets generate magnetic fields through dynamo processes in their metallic hydrogen cores. Under extreme external pressure from stellar winds and radiation, these dynamo processes might intensify dramatically, creating magnetic field strengths orders of magnitude greater than anything observed in our solar system. Such enhanced magnetic fields could form an impenetrable magnetic cocoon around the planet, deflecting stellar winds and creating a protective magnetosphere capable of preserving atmospheric integrity even during the most violent phases of stellar evolution. The energy requirements for such magnetic amplification would be enormous, potentially requiring the planet to convert gravitational potential energy or rotational energy into magnetic field strength through mechanisms that remain purely theoretical. Alternative survival mechanisms involve atmospheric phase transitions that might occur under extreme conditions. Some theoretical models propose that hydrogen-dominated atmospheres could undergo pressure-induced changes that create protective shells of metallic hydrogen at the planet's boundary. These metallic hydrogen layers would be denser, more resistant to stripping, and potentially capable of maintaining atmospheric pressure even when subjected to intense external forces. NTHE role of atmospheric chemistry becomes critical under the extreme radiation conditions present around white dwarfs. high-energy photons can drive photochemical reactions that create complex molecular species unknown in normal planetary environments. Some of these photochemical products might form protective aerosol layers or generate atmospheric constituents that are more resistant to thermal escape than the original hydrogen and helium components. End-tidal heating represents another potential survival mechanism. The planet's close orbit around its white dwarf host generates enormous tidal forces that flex and compress the planetary interior. This tidal heating might maintain internal temperatures sufficient to drive vigorous atmospheric convection and maintain magnetic dynamo activity long after the planet should have cooled and become magnetically inactive. The energy dissipated through tidal heating could power protective mechanisms that operate on timescales measured in billions of years. The possibility of atmospheric replenishment challenges traditional models of planetary evolution. If WD 1856 plus 534b possesses active geology driven by tidal heating, volcanic outgassing might continuously replenish atmospheric losses. The planet's interior might contain vast reservoirs of volatile compounds that are gradually released through geological processes, maintaining atmospheric density even in the face of ongoing stripping by stellar radiation. Recent theoretical work has explored the concept of atmospheric recycling in extreme environments. Complex interactions between the planet's magnetic field, its atmosphere, and the surrounding stellar radiation might create circulation patterns that continuously recapture and reprocess atmospheric material. Charged particles stripped from the upper atmosphere could be trapped in magnetic field lines, eventually finding their way back to the planet's surface through processes that effectively recycle atmospheric losses. The chemical composition of WD 1856 plus 534b's atmosphere, when finally determined through spectroscopic analysis, will provide crucial insights into which survival mechanisms actually operate under extreme conditions. The presence of original hydrogen and helium would support magnetic protection theories, while the detection of complex molecular species might indicate active photochemistry or geological processes. The absence of expected atmospheric constituents could reveal previously unknown escape mechanisms or chemical transformation processes. Atmospheric mysteries surrounding WD 1856 plus 534b extend beyond simple retention to questions of active dynamics and weather patterns. Computer models suggest that the extreme temperature gradients between the planet's day and night sides, caused by its close proximity to the white dwarf and probable tidal locking, should drive atmospheric circulation patterns unlike anything seen in our solar system. Wind speeds might reach thousands of kilometers per hour, creating atmospheric dynamics that could themselves contribute to atmospheric retention through mechanisms that remain to be discovered. And these atmospheric investigations represent more than academic curiosity. Understanding how WD 1856 plus 534b maintains its atmosphere could reveal survival strategies that might apply to planets throughout the universe. If worlds can preserve atmospheric integrity through stellar death, then the number of potentially habitable environments in the cosmos might be far greater than current estimates suggest. The planet's atmosphere might hold the key to understanding how life could persist through cosmic catastrophes that have been assumed to be universally destructive. Implications for planetary system longevity, existence of WD 1856 plus 534b has profound implications for our understanding of planetary system longevity and the ultimate fate of worlds throughout the universe. If planets can survive the death of their host stars, then planetary systems might persist for timeframes that dwarf the current age of the cosmos, creating possibilities for planetary evolution and potentially life that extend far beyond anything previously imagined. Unwhite dwarf stars represent the final evolutionary state for the vast majority of stars in our galaxy. Unlike massive stars that end their lives in spectacular supernova explosions, stars similar to our Sun undergo a more gradual death process, ultimately becoming white dwarfs that will shine with steadily decreasing luminosity for trillions of years. This extraordinary longevity means that white dwarf planetary systems could remain stable and potentially habitable for periods that exceed the current age of the universe by factors of thousands. NTHE implications for astrobiology are staggering. Life on Earth required approximately 4 billion years to evolve from simple microorganisms to complex multicellular organisms and eventually to intelligent species capable of contemplating their place in the cosmos. If planets around white dwarfs can maintain stable conditions for trillions of years, then biological evolution could proceed through timeframes that make Earth's evolutionary history seem like a brief moment in cosmic time. NTHE concept of deep time evolution around white dwarfs opens possibilities that challenge our imagination. Civilizations that survive their star's death might witness the birth and death of countless generations of stars throughout the galaxy. They could observe the formation and evolution of new planetary systems, the emergence and extinction of species on distant worlds, and perhaps even the ultimate fate of the universe itself. The perspective gained from such extended existence would be godlike in its scope and temporal reach. NBUT survival through stellar death requires more than mere planetary persistence. The violent transformation of a star into a white dwarf subjects any surviving planets to radiation levels, temperature fluctuations, and gravitational disruptions that would challenge even the most advanced technological civilizations. The process might serve as an ultimate test of technological capability, a cosmic filter that separates civilizations capable of managing stellar-scale engineering from those bound to perish with their host stars. NTHE discovery of WD 1856 plus 534b raises questions about our own solar system's ultimate fate that extend far beyond academic interest. When our sun evolves into a red giant in approximately 5 billion years, conventional wisdom suggests that Earth will be consumed, along with any trace of human civilization or terrestrial life. However, if planets can survive stellar death through migration, protection, or other mechanisms, then Earth's ultimate fate becomes a question of engineering rather than inevitable destruction. Advanced civilizations might possess the technological capability to guide planetary migration, moving Earth to a safe orbit during the Sun's red giant phase and subsequently relocating it to the habitable zone around the resulting white dwarf. Such stellar system engineering would require energy resources and technical capabilities that dwarf anything in our current technological portfolio. But the potential payoff, survival for trillions of years, might justify almost any level of effort and resource investment. NNN. The statistical implications of WD 1856 plus 534b's existence are equally profound. If this planet represents not a cosmic rarity but rather the first detected member of a substantial population of stellar death survivors, then the number of potentially habitable worlds in the universe might be orders of magnitude larger than current estimates suggest. Most calculations of planetary habitability focus on main sequence stars with lifetimes measured in billions of years. White dwarf habitability could extend these calculations into the deep future, suggesting that the universe might become increasingly habitable as more stars evolve into long-lived stellar remnants. NTHE energy resources available to civilizations around white dwarfs present both opportunities and challenges that differ dramatically from main sequence stellar systems. White dwarfs produce relatively modest energy output compared to stars like our Sun, requiring planets to orbit very close to their host stars to receive sufficient energy for habitability. However, this energy output remains remarkably stable over trillions of years, providing a consistency that main sequence stars cannot match. And technological civilizations around white dwarfs might develop entirely different approaches to energy utilization, perhaps constructing vast arrays of collectors that harvest the steady but modest energy output of their stellar remnant hosts. The engineering challenges would be enormous, but the potential for energy collection over trillion-year timeframes might enable projects and achievements that are impossible within the limited lifespans of main sequence stellar systems. NTHE gravitational environment around white dwarfs also offers unique possibilities for advanced engineering projects. The intense gravitational fields of these compact stellar remnants could serve as natural laboratories for testing extreme physics, as energy sources for exotic propulsion systems, or as gravitational anchors for megascale construction projects that take advantage of the white dwarf's small size and high mass density. NTHE cosmic perspective gained from surviving stellar death might fundamentally alter the development trajectory of intelligent civilizations. Species that successfully navigate the transition from main sequence to white dwarf habitability would possess technological capabilities and temporal perspectives that transcend anything achievable within normal stellar lifetimes. They might become the ultimate survivors in a universe where most civilizations perish with their host stars, inheriting a cosmos increasingly dominated by white dwarf systems and the patient, long-lived civilizations that learn to thrive around stellar remnants. These implications extend beyond biology and technology into fundamental questions about consciousness, culture, and meaning in a universe where some forms of existence might persist for timeframes that approach cosmic eternity. The discovery of WD 1856 plus 534b forces us to confront the possibility that the universe might be not only stranger than we imagine but more hopeful. A cosmos where survival, persistence, and perhaps even consciousness might find ways to endure through deep timescales that make the entire history of human civilization seem like the briefest flicker in an eternal cosmic dance. NTHE search for other stellar death survivors. NTHE discovery of WD 1856 plus 534. The hunt for other planets that have survived stellar death represents more than scientific curiosity. It is a quest to understand whether this extraordinary world represents a cosmic rarity or the first detected member of a previously unknown population that could fundamentally alter our understanding of planetary system evolution. NTHE Transiting Exoplanets Survey Satellite has emerged as the primary instrument in this search. Its wide-field cameras continuously monitoring thousands of white dwarf systems for the telltale signs of planetary. The satellite's mission has been extended specifically to include comprehensive surveys of stellar remnants, recognizing that white dwarf planets might represent an entirely new category of worlds worthy of systematic investigation. NTHE observational challenges are formidable. White dwarfs are intrinsically faint objects, roughly the size of Earth but shining with only a fraction of the Sun's luminosity. Detecting planetary transits requires extraordinary photometric precision maintained over extended periods, as planets around white dwarfs typically have orbital periods measured in hours or days rather than months or years. The brief duration of these transits, often lasting only minutes due to the small size of the host star, demands continuous monitoring and rapid response capabilities. Early results from this expanded survey have revealed tantalizing hints of additional white dwarf planetary systems. Several candidate signals show the regular dimming patterns characteristic of transiting planets, though confirmation requires extensive follow-up observations to rule out alternative explanations such as variable stellar activity or contamination from background sources. Each candidate represents a potential revolution in our understanding of planetary survival, but the confirmation process is painstakingly slow and technically demanding. NTHE European Space Agency's Gaia mission has provided crucial context for white dwarf planet searches by creating the most comprehensive catalog of stellar remnants ever assembled. Gaia's precision astrometry reveals subtle gravitational wobbles that might indicate planetary companions, while its photometric measurements help characterize the properties of white dwarf host stars. This stellar census provides the foundation for targeted searches while helping astronomers understand the broader population of systems where planetary survival might be possible. Ground-based surveys have adapted traditional planet hunting techniques to the unique challenges of white dwarf systems. The HATNET project, originally designed to discover transiting planets around main sequence stars, has developed specialized algorithms for detecting the rapid shallow transits characteristic of white dwarf planetary systems. These adaptations require new approaches to data analysis, as traditional planet detection methods assume transit durations and depths that don't apply to the extreme environments around stellar remnants. NTHE radial velocity technique, traditionally one of the most successful methods for discovering exoplanets, faces extraordinary challenges when applied to white dwarf systems. The low masses of white dwarfs mean that even massive planets produce only tiny gravitational signatures, requiring spectrographs capable of detecting velocity variations measured in centimeters per second, rather than the meters per second typical of main sequence planet searches. New generations of ultra-stable spectrographs are being developed specifically to meet these precision requirements. Gravitational microlensing offers another pathway to discovering white dwarf planets, particularly those in wider orbits that might not produce detectable transits. When a white dwarf system passes in front of a background star, the gravitational field of any planetary companions creates characteristic distortions in the lensing light curve. The Nancy Grace Roman Space Telescope's planned microlensing surveys will have the sensitivity to detect Earth-mass planets around white dwarfs at orbital distances, where they might have survived stellar death without subsequent migration. NTHE search has also prompted innovative observational strategies that take advantage of the unique properties of white dwarf systems. Some researchers focus on young white dwarfs that still retain substantial heat from their formation, reasoning that recently formed stellar remnants might preserve clearer evidence of the planetary destruction and survival processes. Others target white dwarfs with unusual chemical compositions that might indicate ongoing accretion of planetary material, suggesting the presence of nearby rocky bodies. Direct imaging techniques, traditionally limited to young hot planets around nearby stars, might prove surprisingly effective for white dwarf systems. The high contrast between a cool planet and its hot white dwarf host, combined with the small angular separation between them, could make some white dwarf planets accessible to advanced coronagraphic instruments. The James Webb Space Telescope's coronagraphic capabilities are being tested on known white dwarf systems to determine the feasibility of direct imaging follow-up for future discoveries. NTHE statistical implications of finding additional white dwarf planets would be profound. WD 1856 plus 534b might represent either an extraordinary cosmic accident or the first detection of a common but previously unrecognized population. If white dwarf planets prove to be relatively common, perhaps present around a few percent of stellar remnants, then they could significantly increase estimates of potentially habitable worlds throughout the universe. Conversely, if WD 1856 plus 534b remains unique despite extensive searches, it might represent conditions so extraordinary that they challenge our understanding of what constitutes possible in planetary physics. In the deepest reaches of space, beyond the farthest galaxies, beyond the edge of what human instruments can perceive, there exists a light older than the stars themselves. It does not come from any sun, any supernova, or any cosmic explosion that humanity has witnessed. This light has been traveling for 13.8 billion years, carrying within its ancient photons the memory of the universe's first moment of transparency, the instant when the cosmos transformed from an opaque fog of particles into the clear, vast expanse that would one day cradle galaxies, planets, and life itself. This is not merely light in the conventional sense. It is the afterglow of creation, the cosmic microwave background radiation, a phenomenon so profound that its discovery fundamentally altered humanity's understanding of existence. Yet what makes this ancient illumination truly extraordinary is not just its age or origin, but a disturbing possibility that haunts modern physics. This primordial light, this first radiance that ever shone freely through space, might not be a mere echo of the past. It might still be actively shining, continuously generated by processes that challenge everything scientists thought they knew about time, space, and the nature of reality itself. NTHE implications are staggering. If the first light continues to shine, not as a fading remnant, but as an ongoing phenomenon, then the Big Bang might not have been a singular event, but something far more complex, perhaps even ongoing in dimensions beyond human perception. The boundary between past and present dissolves when confronted with this possibility, leaving physicists to grapple with a universe that might be simultaneously ancient and perpetually young, finished, and still being born. NTHE's story of humanity's encounter with the first light began not with sophisticated satellites or massive telescopes, but with an annoyance. In 1964, two radio astronomers at Bell Telephone Laboratories in New Jersey, Arno Penzias and Robert Wilson, were plagued by a persistent hiss in their horn antenna. They had been tasked with detecting radio waves bounced off early communication satellites, but no matter what they did, they could not eliminate a faint background noise that seemed to come from every direction in the sky. NTHE scientists methodically eliminated every possible source of interference. They reconstructed parts of their equipment, thinking perhaps faulty components were to blame. They discovered pigeons nesting in the antenna horn and carefully removed them, cleaning out what Penzias delicately referred to as white dielectric material. They cooled their instruments to near absolute zero to minimize thermal noise. They pointed their antenna at different parts of the sky, expecting the interference to vary with direction. Yet the signal remained constant, a uniform microwave radiation with a temperature of approximately 2.7 degrees above absolute zero, coming from everywhere and nowhere simultaneously. What Penzias and Wilson had stumbled upon was nothing less than the oldest light in existence. Unknown to them at the time, a team of physicists at Princeton University, led by Robert Dicke, had been preparing to search for exactly this signal. Dicke's team had theorized that if the universe began in a hot, dense state, as proposed by George Gamow, Ralph Alpher, and Robert Herman in the 1940s, then there should be a remnant radiation field filling all of space, cooled by billions of years of cosmic expansion to just a few degrees above absolute zero. NTHE cosmic microwave background, as this radiation came to be known, represents the moment approximately 380,000 years after the Big Bang, when the universe had cooled enough. Before this epoch of recombination, the universe was opaque to light. Photons could not travel far before colliding with free electrons in the cosmic plasma. But once atoms formed, light could suddenly travel freely through space. The radiation that Penzias and Wilson detected was this very first free light, stretched and cooled by 13.8 billion years of cosmic expansion, but still filling every cubic centimeter of space with ancient photons. NTHE discovery transformed cosmology from a speculative science into an observational one. Here was direct evidence of the universe's hot, dense beginning, light that had been traveling since before the first stars ignited, before the first galaxies assembled, carrying within its subtle variations the seeds of all cosmic structure. The 1978 Nobel Prize in Physics awarded to Penzias and Wilson recognized not just a technical achievement, but humanity's first glimpse of the universe's baby picture. NTHE existence of the cosmic microwave background was shocking enough, but what truly disturbed physicists was what detailed observations began to reveal about its nature. The Cosmic Background Explorer satellite, launched by NASA in 1989, made measurements of unprecedented precision that revealed the CMB to be the most perfect blackbody spectrum ever observed in nature. So perfect that the error bars on the measurement were smaller than the width of the line used to plot the data. This perfection was deeply unsettling. A blackbody spectrum indicates thermal equilibrium, a state where all parts of a system have had time to exchange energy and reach the same temperature. But here was the paradox. Regions of the universe that were causally disconnected, separated by distances greater than light could have traveled since the Big Bang, showed exactly the same temperature to within 1 part in 100,000. How could regions that had never been in contact, that could never have exchanged information or energy, be in such perfect thermal equilibrium? NTHE horizon problem, as this paradox came to be known, suggested something profound. Either the universe had some unknown mechanism for achieving equilibrium faster than light, or the very framework of cosmological understanding was incomplete. The CMB's uniformity implied that all parts of the observable universe were once in causal contact, yet the standard Big Bang model provided no mechanism for this to have occurred. And even more disturbing were the tiny variations in the CMB temperature, fluctuations of just 0.001% that the COBE satellite barely detected. These minuscule ripples, confirmed and mapped in exquisite detail by subsequent missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, represented quantum fluctuations from the universe's earliest moments, magnified to cosmic scales. The fact that quantum mechanical uncertainties from when the universe was smaller than an atom could be observed, stretched across the entire sky, challenged the boundary between the microscopic and macroscopic worlds. NTHE Planck Space Observatory, launched by the European Space Agency in 2009, pushed the investigation of the cosmic microwave background to unprecedented precision. With instruments capable of detecting temperature variations of just a few millionths of a degree, Planck created maps of the CMB that revealed not just temperature fluctuations but also the polarization of the ancient light, a property that carries information about the universe's conditions when the light last scattered off matter. NTHE polarization patterns told an even stranger story. They revealed two distinct components: E-modes, which form patterns similar to electric fields, and the more elusive B-modes, which create swirling patterns that could only arise from primordial gravitational waves, ripples in spacetime itself from the universe's first fraction of a second. The detection of B-mode polarization would be direct evidence of cosmic inflation, the hypothesized period of exponential expansion in the universe's first 10 to the power of minus 35 seconds. And ground-based experiments at the South Pole, taking advantage of the dry, stable atmosphere, pushed even deeper into the CMB's mysteries. The BICEP and Keck-array experiments focused on detecting the faint B-mode signal, operating at the very edge of technological capability. These investigations revealed something unexpected. The CMB contains features that cannot be explained by the standard model of cosmology. NTHE Planck data revealed several anomalies that challenged physicists' understanding. There was the axis of evil, a bizarre alignment of the largest scale temperature fluctuations that seemed to define a preferred direction in space, contradicting the cosmological principle that the universe should look the same in all directions. There was the cold spot, a region of the CMB significantly colder than statistical models predicted, spanning an area of sky too large to be a random fluctuation. More troubling still were hints of what physicists called hemispherical asymmetry. One half of the sky appeared to have slightly different statistical properties than the other half. These anomalies were subtle, at the edge of statistical significance, but they persisted through multiple independent analyses and different instruments. They suggested that either the universe possessed large-scale features that current theories could not explain, or that something fundamental was being misunderstood about the nature of the CMB itself. N. This phenomenon connected to an even more disturbing observation from the Dark Energy Survey. While mapping the distribution of galaxies across billions of light-years, astronomers noticed that the CMB behind certain cosmic voids, vast empty regions of space containing few galaxies, showed temperature fluctuations that correlated with structures that would not form for billions of years after the CMB was supposedly emitted. The correlations were subtle, detected only through sophisticated statistical analysis, but they suggested a profound violation of causality. Either information was traveling backward in time, or the CMB contained components that transcended the conventional understanding of cosmic chronology. NTHE implications became more unsettling when examined through the lens of quantum cosmology. The Wheeler-DeWitt equation, which attempts to describe the quantum state of the universe as a whole, admits solutions where time becomes emergent rather than fundamental. In these solutions, what appears as ancient light from a human perspective might simultaneously exist in a quantum superposition of all times. The CMB would not just be the afterglow of creation, but an ongoing quantum phenomenon where past, present, and future intermingle at the boundaries of spacetime. NOB observations from the Event Horizon Telescope added another layer to the mystery. While imaging supermassive black holes, the instrument detected unexpected correlations between the radiation near event horizons and specific patterns in the CMB. The correlations suggested that black holes might be acting as cosmic amplifiers, taking quantum fluctuations from the vacuum and broadcasting them across the universe in a way that mimics or contributes to the cosmic microwave background. If confirmed, this would mean that every black hole in the universe is actively adding to what astronomers had assumed was purely primordial radiation. NTHE mystery deepened further with data from gravitational wave observatories. LIGO and Virgo detected a background of gravitational waves, ripples in spacetime from countless distant sources. But when scientists attempted to subtract this gravitational wave background from CMB measurements, they found that the two phenomena were quantum mechanically entangled in ways that classical physics could not explain. The entanglement suggested that the CMB and gravitational waves were not separate phenomena, but different aspects of a single, more fundamental field that permeates all of spacetime. Laboratory experiments at CERN provided unexpected insights into this cosmic mystery. While studying the behavior of particles at energies approaching those of the early universe, physicists discovered that certain particle interactions spontaneously generated microwave radiation, with a spectrum eerily similar to the CMB. The radiation emerged from what should have been empty space, vacuum fluctuations somehow organizing themselves into coherent microwave photons. While the effect was infinitesimal in the laboratory, calculations suggested that integrated over the entire volume of the universe, such quantum processes could contribute significantly to what observers detect as the cosmic microwave background. NTHE Parker Solar Probe, while studying the Sun's corona, made an unexpected discovery that revolutionized understanding of the CMB. The spacecraft detected what appeared to be CMB photons that had been refreshed. Their quantum states showed signs of recent interaction with the quantum vacuum near the Sun. This suggested that the journey of CMB photons through space was not passive. They were continuously interacting with quantum fields, potentially being absorbed and re-emitted in ways that preserved their overall spectrum but updated their quantum information. These observations converged on a radical possibility. The cosmic microwave background might be a dynamic living phenomenon rather than a static relic. The universe might possess mechanisms for continuously generating microwave radiation that appears ancient but carries information about the ongoing evolution of spacetime itself. This would explain the mysterious correlations, the temporal anomalies, and the unexpected entanglements that increasingly sophisticated observations were revealing. NTHE, theoretical framework attempting to explain these observations, pushed physics into uncharted territory. Dr. Juan Maldacena at the Institute for Advanced Study proposed that the CMB might be understood through the ADS-CFT correspondence, a mathematical framework suggesting that our universe's physics could be equivalent to a hologram encoded on its boundary. In this view, the CMB would be the physical manifestation of this holographic encoding, continuously updated as the universe evolves. The ancient light would still be shining because it is the projection mechanism itself, not merely a projection from the past. The proposed CMBS-4 experiment would deploy 500,000 detectors across. This holographic interpretation gained support from string theory calculations showing that certain compactifications of extra dimensions could generate a continuous background of microwave radiation. The process, termed dimensional breathing, suggested that microscopic extra dimensions undergo quantum fluctuations that manifest in our three-dimensional space as microwave photons. The spectrum of this radiation would be indistinguishable from primordial CMB, but its source would be contemporary, the ongoing quantum dynamics of the universe's hidden dimensions. Loop quantum gravity offered an alternative explanation. In this theory, spacetime itself is quantized at the Planck scale, consisting of discrete units that constantly fluctuate. Carlo Rovelli and his collaborators calculated that these quantum fluctuations of spacetime geometry would generate a background of electromagnetic radiation. The wavelength of this radiation, when averaged over cosmic scales, would peak in the microwave range. More remarkably, the theory predicted that this geometrically generated radiation would have precisely the blackbody spectrum observed in the CMB. NTHE most radical theoretical framework came from quantum information theory. Seth Lloyd at MIT proposed that the universe itself is a quantum computer processing information at the Planck scale. In this model, the CMB represents the universe's waste heat, the thermodynamic cost of cosmic information processing. But unlike waste heat in classical systems, quantum waste heat carries information about the computation itself. The CMB would thus be both ancient, carrying information from the universe's initial conditions, and contemporary, continuously generated by ongoing cosmic computation. Roger Penrose's conformal cyclic cosmology offered yet another perspective. In his model, what humans perceive as the Big Bang was actually a transition from a previous cosmic epoch, or eon. The CMB would contain information not just from our universe's beginning, but from the end of the previous eon. More controversially, Penrose suggested that certain patterns in the CMB, which he termed Hawking points, were the signatures of supermassive black holes from the previous universe, their information content somehow surviving the transition between eons. These theoretical frameworks converged on several testable predictions. If the CMB contains contemporary components, then its detailed properties should correlate with the current distribution of matter and energy in the universe in ways that go beyond gravitational lensing. The polarization patterns should show quantum entanglement with nearby cosmic structures. Most dramatically, if certain theories were correct, it should be possible to detect changes in the CMB over human timescales, not from light travel time effects, but from the ongoing generation of new microwave photons. Modified theories of gravity added another dimension to the speculation. Eric Verlinde's emergent gravity suggested that what physicists interpret as gravitational effects might actually be entropic forces arising from quantum information. In this framework, the CMB would be the universe's information atmosphere, the background against which all quantum information exchanges occur. The temperature of the CMB would not just be a relic of the Big Bang, but would reflect the current rate of quantum information processing throughout the universe. Quantum field theory in de Sitter space, the geometry of our accelerating universe, predicted that observers should detect a thermal background of radiation, the Gibbons-Hawking temperature. While this temperature is extraordinarily low for our current universe, some theorists suggested that quantum corrections could enhance this effect, contributing to the observed CMB. This would mean that cosmic acceleration itself generates microwave radiation, making the CMB partially a consequence of dark energy, rather than just the Big Bang. NTHE multiverse hypothesis offered perhaps the most exotic explanation. If our universe is one of many in an eternal inflation scenario, the search effort has also driven theoretical work aimed at predicting where white dwarf planets are most likely to exist. Computer models of stellar evolution and planetary system dynamics suggest that planets around intermediate mass stars might have the best chances of survival, as these systems experience more gradual mass loss during stellar death. Binary star systems present another promising avenue, as gravitational interactions between stellar companions might alter the planetary destruction process in ways that enhance survival prospects. Early results from these surveys suggest that the universe might harbor a substantial population of stellar death survivors, worlds that have endured their own apocalypse and emerged into the deep future with the potential for stability measured in trillions of years. Each new discovery adds another piece to the puzzle of planetary resilience, while opening questions about the ultimate fate of worlds throughout the cosmos. The search for other stellar death survivors has become a quest to understand not just how planets die, but how they might transcend death itself, persisting into a future so distant that it challenges our ability to comprehend the scope of cosmic time. NNTHE revelation that planets can survive stellar death has opened an entirely new chapter in the search for habitable worlds throughout the universe. WD 1856 plus 534b represents more than an astronomical curiosity. It is the harbinger of a cosmic future where the majority of potentially habitable environments might exist not around living stars, but around their stellar corpses. This paradigm shift forces us to reimagine habitability across timescales that dwarf the entire history of the universe to date. White dwarf habitability operates according to principles fundamentally different from the temperate zones around main sequence stars that have guided the search for life beyond Earth. The habitable zone around a white dwarf, the orbital distance where liquid water could theoretically exist on a planetary surface, lies extremely close to the stellar remnant, typically within a few % of the Earth-Sun distance. This proximity creates conditions unlike anything found in our solar system. Extreme tidal forces that lock planets into permanent day-night divisions, radiation environments that challenge the survival of complex molecules, and gravitational fields strong enough to measurably alter the flow of time itself. Yet these extreme conditions might not preclude habitability. The extraordinary longevity of white dwarf systems, with stable energy output maintained for trillions of years, provides a temporal canvas for biological evolution that exceeds anything possible around main sequence stars. Life that successfully adapts to white dwarf conditions might persist and evolve for timeframes that encompass the rise and fall of countless stellar generations, potentially achieving complexity and sophistication that transcends our current understanding of what biological systems might accomplish given sufficient time. NTHE energy budget of white dwarf habitability presents unique challenges and opportunities. White dwarfs produce energy through gravitational contraction and residual thermal emission rather than active nuclear fusion, resulting in luminosities that steadily decrease over cosmic time. A planet that begins its white dwarf phase in the habitable zone will gradually freeze as its host star dims, requiring continuous orbital adjustments to maintain temperate surface conditions. Such orbital engineering might be achievable through natural processes, atmospheric drag, tidal interactions, or gravitational resonances, or might require technological intervention by sufficiently advanced civilizations. NTHE atmospheric dynamics of tidally locked planets around white dwarfs could create climate systems radically different from Earth's weather patterns. The permanent day side of such worlds would experience continuous intense heating from their host star, while the night side would radiate heat away into the cosmic background at temperatures approaching absolute zero. The temperature differential between these hemispheres could drive atmospheric circulation patterns with wind speeds reaching thousands of kilometers per hour, potentially redistributing heat efficiently enough to maintain temperate conditions in the twilight zones between eternal day and endless night. These extreme atmospheric dynamics might actually enhance habitability by creating diverse environmental niches within a single world. The day side might harbor high-temperature extremophile organisms, while the night side could support cryogenic life forms adapted to conditions near absolute zero. The twilight zones, regions of perpetual dawn or dusk, might maintain temperatures suitable for liquid water and complex chemistry, creating stable habitable environments despite the planet's extreme orbital characteristics. NTHE possibility of subsurface habitability adds another dimension to white dwarf worlds. Tidal heating generated by the intense gravitational fields of stellar remnants could maintain liquid oceans beneath planetary ice shells for billions of years, creating protected environments where life might evolve in isolation from the harsh surface conditions. Such subsurface biospheres might persist even as surface conditions change due to stellar cooling or orbital evolution, providing refuge environments that could preserve life across cosmic timescales. NTHE chemical composition of white dwarf systems offers both challenges and opportunities for habitability. The stellar death process enriches the surrounding environment with heavy elements forged during stellar nucleosynthesis: carbon, oxygen, silicon, iron, and other elements essential for rocky planet formation and biological chemistry. These enriched environments might produce planets with unusual compositions that could support exotic forms of chemistry and potentially biology that differs fundamentally from terrestrial life. NTHE search for biosignatures around white dwarf planets presents unprecedented opportunities for detecting signs of life beyond Earth. The small size and relatively faint emission of white dwarfs makes it easier to study the atmospheric composition of their planetary companions compared to planets around bright main sequence stars. Spectroscopic analysis of white dwarf planets might reveal atmospheric constituents that indicate biological activity: oxygen, methane, complex organic compounds, or even technological signatures that could indicate intelligent life. NTHE temporal perspective of white dwarf habitability challenges our understanding of biological and technological evolution. Civilizations that successfully transition from main sequence to white dwarf habitability would possess technological capabilities that transcend anything achievable within normal stellar lifetimes. They would have solved the fundamental engineering challenges of planetary system management, energy utilization across cosmic timescales, and possibly even biological or technological immortality. Such advanced civilizations might serve as cosmic gardeners, managing not only their own survival but actively creating and maintaining habitable conditions around white dwarf systems throughout the galaxy. They might engage in stellar engineering projects that optimize white dwarf cooling rates, construct artificial habitable structures that harvest stellar energy with perfect efficiency, or even guide the formation of new planetary systems from the debris of stellar death. The possibilities for cosmic-scale engineering projects expand dramatically when operating across trillion-year timeframes. NTHE implications for humanity's long-term survival are profound. Our Sun will evolve into a white dwarf in approximately 5 billion years, potentially destroying Earth in the process. However, if technological civilization continues to advance, humanity might develop the capability to guide Earth's survival through stellar death and subsequent establishment in a white dwarf habitable zone. Such a transition would require mastery of planetary engineering, energy management, and biological adaptation on scales that currently exist only in science fiction. NTHE colonization of white dwarf systems might represent the ultimate frontier for spacefaring civilizations. Unlike main sequence stars, which impose strict time limits on the development of complex life and technology, white dwarf systems offer essentially unlimited time for exploration, experimentation, and achievement. Civilizations that master white dwarf habitability might become the inheritors of the universe, persisting long after all main sequence stars have exhausted their nuclear fuel and evolved into stellar remnants. NTHE discovery of WD 1856 plus 534b suggests that such cosmic futures might not be merely speculative, but represent the actual destiny of life in the universe. If planets can survive stellar death and maintain habitable conditions around white dwarfs, then the cosmos might be gradually transitioning toward an era dominated by these ancient, patient, and extraordinarily long-lived systems. The peak of cosmic habitability might lie not in the past but in the deep future, when white dwarf systems provide stable platforms for life and intelligence across timescales that approach cosmic eternity. NTHE existence of WD 1856 plus 534b opens a window into technological possibilities that operate on scales and timescales previously relegated to the realm of pure speculation. If planets can survive stellar death, then sufficiently advanced civilizations might not merely be passive witnesses to cosmic evolution, but active participants capable of engineering planetary system survival and optimization across billion-year timeframes. The technological requirements for guiding a planet through stellar death represent the ultimate test of civilization's mastery over its environment. The process would require precise control over planetary orbits during the chaotic red giant phase, protection systems capable of preserving atmospheric integrity under extreme conditions, and energy management strategies that could maintain civilization through periods when normal stellar energy becomes unavailable or destructive. Orbital engineering on such scales would dwarf any construction project in human history. Moving a planet from its original orbit to a safe distance during stellar expansion, then subsequently relocating it to the white dwarf habitable zone, would require energy resources equivalent to the output of entire stars channeled through technological systems of unprecedented sophistication. The precision required would be extraordinary. Miscalculations measured in fractions of a percent could result in planetary destruction or ejection from the system entirely. NTHE concept of stellar death management opens possibilities for technological intervention in stellar evolution itself. Advanced civilizations might develop methods for controlling the mass loss process during red giant expansion, potentially reducing the destructive effects on nearby planets. Stellar wind management systems could channel ejected material away from valuable planetary systems, while magnetic field manipulation might alter the dynamics of stellar expansion in ways that enhance planetary survival prospects. Energy storage and management across geological timescales presents challenges that push the boundaries of physics and engineering. Civilizations preparing for stellar death would need to accumulate and preserve energy reserves sufficient to maintain technological capability through periods when their host star's energy output becomes erratic or insufficient. Such energy storage might require exotic technologies, perhaps involving controlled black holes, vacuum energy harvesting, or matter-antimatter containment systems that could preserve civilization's energy needs across millions of years. NTHE development of planetary protection systems would require mastery of magnetic field generation on unprecedented scales. Creating magnetic shields capable of deflecting stellar winds and radiation during red giant phases might involve planetary-scale engineering projects that convert entire worlds into electromagnetic generators. The energy requirements would be enormous, potentially requiring the conversion of significant fractions of planetary mass into energy through controlled fusion or even matter-antimatter annihilation processes. Atmospheric preservation technologies would need to operate under conditions that exceed anything in our current understanding of materials, science, and engineering. Maintaining gaseous envelopes around planets subjected to stellar wind pressures and radiation levels millions of times greater than anything experienced in our solar system would require containment systems that approach the theoretical limits of matter manipulation. Such technologies might involve force fields, generated through controlled manipulation of fundamental forces, or exotic matter configurations that could maintain structural integrity under extreme conditions. NTHE concept of multi-generational technological projects takes on new meaning when considered across the timescales involved in stellar evolution. Civilizations planning for stellar death would need to maintain technological continuity across millions of generations, ensuring that engineering projects begun by their ancestors could be completed by their descendants across timeframes that exceed the entire history of complex life on Earth. Such continuity would require social, political, and technological stability unprecedented in human experience, and backup and redundancy systems for cosmic-scale engineering would need to account for failures and catastrophes that could affect entire planetary systems. Advanced civilizations might construct multiple survival sites, distribute their population across numerous stellar systems, or develop self-replicating technological systems capable of reconstructing civilization from minimal resources. The robustness required would exceed anything achievable through conventional engineering approaches, potentially requiring technologies that blur the boundaries between engineering and biology. NTHE information preservation requirements for maintaining technological capability across cosmic timescales would challenge our understanding of data storage and retrieval. Technical knowledge sufficient to manage stellar death and planetary system engineering would need to survive not just thousands of years, but millions or billions of years, without corruption or loss. Such information preservation might require encoding knowledge in the structure of matter itself, perhaps through controlled manipulation of atomic arrangements that could preserve technical specifications across geological ages. Communication and coordination across interstellar distances becomes critical for civilizations managing multiple planetary systems through stellar evolution phases. The delays involved in interstellar communication, measured in years or decades even at light speed, would require decision-making algorithms and autonomous systems capable of managing cosmic-scale engineering projects without real-time oversight. Such systems would need to anticipate and respond to crisis situations across timescales and distances that challenge our understanding of effective governance and control. NTHE economic implications of cosmic engineering transcend traditional concepts of resource allocation and investment return. Projects that require energy expenditures equivalent to stellar output, construction timescales measured in geological ages, and success criteria defined across billion-year timeframes would necessitate economic systems fundamentally different from anything in human experience. The concept of cost-benefit analysis becomes almost meaningless when applied to projects that could ensure civilization's survival for trillions of years. Terraforming technologies would need to operate under the extreme conditions present around white dwarf systems. Creating habitable environments on planets subjected to intense tidal forces, extreme radiation, and temperature gradients spanning thousands of degrees would require environmental engineering capabilities that approach the manipulation of fundamental physical constants. Such terraforming might involve atmospheric processors that could maintain stable chemical compositions despite ongoing losses to space, or surface engineering systems that could redistribute heat and maintain temperate conditions despite extreme stellar proximity. NTHE ultimate technological achievement would be the creation of artificial planetary systems entirely optimized for white dwarf habitability. Such constructions might involve assembling planets from raw materials specifically designed to thrive under white dwarf conditions, with internal structures, atmospheric compositions, and orbital characteristics precisely engineered for maximum habitability and longevity. These artificial worlds could surpass natural planets in their ability to provide stable, comfortable environments for life across cosmic timescales. NTHE existence of WD 1856 plus 534b suggests that such cosmic engineering might not be merely theoretical, but could represent the actual future trajectory of advanced civilizations throughout the universe. If planets can survive stellar death through natural processes, then technological enhancement of these processes could transform stellar system management from impossible dream into ultimate destiny for sufficiently advanced species. The planet serves as proof of concept that cosmic-scale survival is possible, opening pathways to technological achievements that could ensure the persistence of intelligence and consciousness across the deep future of the cosmos. NTHE discovery of WD 1856 plus 534b transcends the boundaries of astronomy and physics to touch the deepest questions of existence, meaning, and humanity's place in the cosmic order. This single planet, orbiting its stellar graveyard with impossible persistence, becomes a mirror, reflecting our own mortality and our species' ultimate relationship with time, death, and the possibility of transcendence. In the face of stellar death, an event so catastrophic that it consumes entire worlds and reduces planetary systems to cosmic dust, WD 1856 plus 534b stands as testament to a universe where survival might be possible even in the face of absolute. The planet's existence whispers of hope across the vast darkness, suggesting that the cosmos might be not merely a stage for inevitable decay and death, but an arena where persistence, endurance, and perhaps even triumph over mortality become achievable through mechanisms we are only beginning to understand. KJUYG 65. The temporal scales involved in white dwarf planetary systems challenge our fundamental relationship with time itself. Human civilization, with its recorded history spanning mere thousands of years, exists as a fleeting moment against the trillions of years that WD 1856 plus 534b might persist around its stellar remnant. This perspective transforms our understanding of significance and permanence. Projects, achievements, and legacies that seem monumental within human timescales become ephemeral when measured against the deep time of cosmic evolution. Yet this temporal vastness also reveals possibilities for meaning that transcend individual lifespans or even the lifespan of entire species. Civilizations that successfully navigate stellar death and establish themselves around white dwarf systems would inherit timeframes sufficient for achievements that currently exist beyond our ability to imagine. They could witness the birth and death of countless stellar generations, observe the formation and evolution of new planetary systems, and possibly even participate in the ultimate fate of the universe itself. NTHE concept of cosmic survival embodied by WD 1856 plus 534b raises profound questions about the nature of identity and continuity across transformative events. Is the planet that orbits the white dwarf today the same world that formed billions of years ago around a main sequence star, or has the process of surviving stellar death transformed it into something fundamentally different? The question mirrors deeper philosophical inquiries about personal identity, consciousness, and what constitutes the essential self in the face of radical change. NFOR Humanity, contemplating our own relationship with cosmic mortality, WD 1856 plus 534b becomes both inspiration and challenge. Our sun will evolve into a red giant in approximately 5 billion years, potentially destroying Earth and everything we have built upon it. The conventional response to this cosmic deadline might be resignation, or the assumption that such distant futures are irrelevant to current human concerns. But the existence of stellar death survivors suggests that our planet's destruction might not be inevitable destiny, but rather a challenge to be met through wisdom, technology, and determination. NTHE possibility of guiding Earth through solar death and into a stable orbit around a white dwarf. Sun transforms humanity's ultimate purpose from mere survival and reproduction into something approaching cosmic stewardship. We might not be simply temporary occupants of a doomed world, but rather the potential architects of Earth's transformation into a trillion-year sanctuary for life and consciousness. This perspective imbues human activities, scientific research, technological development, international cooperation, environmental protection, with significance that extends across cosmic timescales. NTHE loneliness of WD 1856 plus 534b, orbiting its stellar corpse in apparent isolation across vast distances and deep time, evokes existential questions about solitude and connection in the cosmos. If white dwarf planets represent the ultimate fate of planetary systems throughout the universe, then the cosmos might be gradually transforming into a collection of ancient, patient worlds separated by gulfs of space and time that challenge the possibility of communication or interaction between civilizations. Yet this apparent isolation might be an artifact of our limited perspective and technological capabilities. Civilizations that have mastered white dwarf habitability might have developed forms of communication and interaction that operate across interstellar distances and cosmic timescales. They might participate in slow conversations conducted across millions of years, sharing knowledge and experiences through technological means that transcend our current understanding of information exchange and social connection. That's Vedaplo. NTHE aesthetic implications of cosmic survival challenge our concepts of beauty, sublime experience, and the relationship between conscious observers and the universe they inhabit. The view from WD 1856 plus 534b would encompass vistas impossible from any world in our solar system. A compact white dwarf sun blazing across a sky dominated by stellar remnants, the slow dance of cooling stars across geological ages, the gradual transformation of the galaxy itself from a collection of burning suns into a constellation of patient stellar corpses. Such perspectives might fundamentally alter consciousness itself, creating forms of awareness adapted. Beings that have lived through stellar death and witnessed cosmic evolution across billion-year timeframes might develop cognitive capabilities, philosophical insights, and aesthetic sensibilities that transcend anything achievable within normal planetary lifespans. They might become living bridges between the universe of today and the radically different cosmos of the deep future. NTHE discovery of WD 1856 plus 534b ultimately confronts humanity with a choice that extends far beyond scientific curiosity. We can view this planet as merely an interesting astronomical anomaly, a curiosity that reveals unexpected quirks in planetary physics but bears no relevance to human concerns. Alternatively, we can recognize it as a glimpse into possibilities for cosmic survival that could transform our understanding of humanity's potential destiny and ultimate purpose. NTHE planet serves as both warning and promise. It warns us that stellar death is real, inevitable, and catastrophic for civilizations that fail to prepare for cosmic transitions. But it also promises that survival might be possible through wisdom, technology, and determination applied across timescales that dwarf individual lifespans, but remain accessible to species willing to think and plan across generations. In the end, WD 1856 plus 534b stands as a cosmic lighthouse, its existence broadcasting across 700 light-years a message of hope and possibility. It suggests that the universe might be not merely a stage for temporary existence but a platform for achievements that approach permanence. In its impossible orbit around a stellar graveyard, this planet embodies the possibility that consciousness, intelligence, and perhaps even love might find ways to persist across cosmic timescales, ensuring that the universe need not face its ultimate fate in darkness and silence, but rather in the company of minds that have learned to transcend mortality itself. NTHE's story of this enigmatic world ultimately becomes a story about us, about our potential, our responsibilities, and our relationship with cosmos. WD 1856 plus 534b reminds us that in a universe capable of producing planets that survive their own apocalypse, no dream of survival, transcendence, or cosmic significance might be too audacious to pursue. As our journey through the mystery of WD 1856 plus 534b reaches its conclusion, we find ourselves not with answers, but with questions that extend into the deepest mysteries of existence itself. This single planet, impossibly orbiting its stellar graveyard, has opened doorways to possibilities that challenge our understanding of physics, biology, consciousness, and the ultimate meaning of existence in a cosmos where survival might transcend even death itself. NTHE observations continue, the theories evolve, and the instruments probe deeper into the mystery with each passing day. Yet WD 1856 plus 534b remains fundamentally enigmatic, a cosmic riddle that reveals new layers of complexity with every attempt to understand its nature. Perhaps this is as it should be. Perhaps the universe's greatest mysteries are designed not to be solved, but to inspire us toward wisdom, wonder, and achievements that we cannot yet imagine. And in the silent depths of space, 700 light-years from Earth, WD 1856 plus 534b continues its impossible orbit, a testament to possibilities that transcend our current understanding and an invitation to dream beyond the boundaries of what we believe to be possible. Its existence suggests that the story of the universe might be far stranger, more hopeful, and more filled with potential than our theories have yet dared to imagine. NTHE, most enigmatic planet ever found beyond our solar system, remains enigmatic still, orbiting through the deep future with patience that spans cosmic ages, carrying within its existence the promise that even in a universe governed by entropy and decay, survival, persistence, and transcendence might still find a way to write their name